One of the best aspects of Python comes from the community of people creating different tools and libraries, or working with Python. These tools offer additional functionality to Python. In practice, usually the code you write will use many different libraries. Today, we'll introduce an excellent and commonly used Python library used for analyzing data, Pandas. The Pandas package makes working with data in Python much easier. With Pandas, you can analyze and interact with relatively large data sets and write programs to automate analysis. Pandas allows us to work with data stored in tables. If you're familiar with spreadsheets, you'll likely see the similarities in how the data is organized. It is such a useful tool that sometimes people forget. It's essentially just an extension of the Python and not a different programming language. All right, now we're in a Jupyter notebook. As with all libraries, we can use Pandas by importing the library into our code. We'll go ahead and do that as import pandas as PD. Now we do this as PD as an alias because it's a pretty common practice. This enables us to use useful tools from Pandas, specifically different methods and classes. Writing this with Shift-Enter, we now have the Pandas library imported as PD. Now we can use this inside of a new cell. Now Pandas has these different methods and classes, and you can think of these classes as special data structures. A library like Pandas will have classes that make organizing code and data easier. And you can think of methods as special functions that can work with a variety of things such as classes. Let's see our first Pandas method that you'll get very familiar with called readCSV. We do PD, which is the alias we use for Pandas, and then do a dot, and then we can do read_CSV, and then parentheses. This is an important method from Pandas that we can use to read something like a spreadsheet or a CSV file. For example, we have telecomcustomers.csv file. You can find this data set on Kaggle website, the link in the description. So go ahead, download it, and start practicing with me. The way we can load customer CSV here, we can put in quotes, customer.csv, and note this is the name of the file. This file could contain lots of helpful information about individuals you're trying to market to. We'll go ahead and load this file for analysis. Now, when we run this, we actually get something called a DataFrame. Now we'd like to be able to work with this DataFrame here. So it's very common practice for us to go ahead and assign this to a variable. We'll go ahead and put df at the beginning here, equals, and then the rest of our code. Again, what's going to happen here is that all of this information is going to be assigned to this variable df. When I run this, you'll see when I do Shift-Enter, it disappears, but that's because all the information is in df now. Now that we have this variable df, which is a very commonly used variable name for DataFrames, we can then display the DataFrames content again with display, parentheses, and then df. Now we see our DataFrame here. We can see all this information here in this DataFrame. We also could have put df at the end of a cell and then hit Control-Enter here to run that cell. You see that does effectively the same thing as display. Now Pandas DataFrames are classes that essentially act as a special data structure. We can create or instantiate something from a class. We refer to that thing as an object. The DataFrame here in df has actually created an object, and don't worry if that's a little bit confusing. Now you might be asking, what exactly is a DataFrame? We've seen that DataFrames are the way Pandas stores data. Just like strings, lists, and dictionaries, some of Python's native data types hold data in different ways. Pandas DataFrames hold data in a particular way. DataFrames are a lot like spreadsheets, essentially a table of data. Data are held into rows to represent a single entity. So you can see here, this whole row represents a single entity. We can reference these rows by an index. Here you can see that our index is 0, 1, 2, and so on, all the way down to, looks like 7,042. Now each row has a value in different columns. So we can look at the column names right here on top. These columns are features of each entity. Sometimes the columns of a data frame are referenced as features. You can see what each column represents in the header at the top of this data frame. So you can see here, for example, we have things like the customer ID, their gender, senior citizen, partner, tenure, etc. Some of this information might be more relevant if we knew what this data was about. But this usually will give us an idea of what these columns represent. We'll be going over in more detail about data frames later in this course. Now going back to our code, you should know that DataFrame objects have special functions attached to them. These are called methods and are generally used with a dot notation. Let's go ahead and try that out. The way we call these methods is doing a df, which is a variable that the DataFrame is assigned to, and then we'll use the dot notation and then the name of the method. The first method we're going to try out is head, and then we end with the parentheses. This method is really useful because if a DataFrame is really quite large, we can instead preview just the first 5 rows with df.head. Writing this with Shift-Enter, you see now we get part of our DataFrame with all those columns, for example, but you'll see that we only get the first 5 rows. Alternatively, we could preview the last 5 lines of our DataFrame by running the command df.tail. This will give us 5 rows, but in this case, the last 5 rows in our dataset. We can also put a number inside df.head or tail, so we get those specific number of rows. So for example, if I do df.head 10, we'll actually get the first 10 rows instead of the first 5. If I do df.tail and put a 1 here, I'll get the very last row. The DataFrame object also has certain properties or attributes that can be accessed with dot notation. For example, we can do something like df.columns, and note that there's no parenthesis at the end of this, and that's because it's a property or attribute. This will give some information about the DataFrame's columns. You can see here, we essentially get something like a list of all the different columns in the DataFrame. So far, we've only seen a small fraction of methods and properties of DataFrames. Some methods require arguments like the file name we specified in the pd_read CSV, but other methods like head and tail don't have any required arguments. But you can provide additional optional arguments to change the method's behaviors. Required and optional arguments vary from method to method. So you might be asking, how do you know which methods and properties exist, and how do we know how to use them? Are we going to have to learn and memorize all of them? Thankfully, the answer is no. Programmers love documentation, which are guidebooks for using libraries and methods. For example, you can actually look at the documentation for Pandas online to find things out like how read CSV method works. When using something like Jupyter Notebook, it's actually really useful because some of the documentation can be accessed directly from Jupyter Notebook. We can do that by doing Shift-Tab. We can access the documentation in Jupyter Notebook by going ahead and writing our method that we care about. So for example, we do pd_read CSV and a Shift-Tab, and we get our documentation right here. I'll go ahead and zoom in so we can see a little better. We can see, for example, all this information about read_CSV. You can see, for example, all the different parameters that we didn't even use, as well as some information about how it's being used. Now what's great about Pandas is that usually there's a lot of documentation available, though that you don't have to know everything. In fact, I promise you I don't know everything as well, but you can basically use this to help you figure out the thing that you need in the time of need. Of course, if you do need it, you can always ask online for help. Now I'll take a closer look at DataFrames and more of Pandas. We mentioned that DataFrames are a lot like spreadsheets, a table of data. We've also learned that you can reference the rows, indoor columns of the DataFrame to interact with a subset of data. We can refer to columns of data in what feels very similar to a dictionary. So we can use the annotation like we use here, similar to a dictionary, where the string is going to be one of the columns. So in this case, doing df and then the square brackets with a string customer ID will get us the column of customer ID. And sure enough, you can see here the different rows of data. So for example, the first ones, 7, 5, 9, and so on, you can see the very first element, I should say the very first row in customer ID is exactly that thing. And it goes all the way down to the end of the data frame. We can also use the dot notation to reference columns. So here we have our df.customerID to reference that column. Now, note that a dot notation can be useful, but it isn't as reliable because the column names might not be compatible with Python code. For example, if we have a name of a column as 2 words with space between them, or the name of the column begins with a number, and we try using dot notations here, we'll end up getting an error, basically saying it's an invalid code. So the only way to access such a column is that we're going to pass it as a string. You notice when we actually call this right here, we're getting a new object called a series. And so you can see this series is basically a list of the data for that column. We can see this more explicitly by first doing our df and then our column, and then assigning that to a variable, in this case, customer IDs. If we see the type here, you can see that it explicitly says a series. This is sort of a mini data frame, but we can also think of it as a specialized dictionary. We can use the index to get a specific value from the series using the bracket notation. If that index is not in the series, there'll be a key error. So here we have our index 0. So customer IDs again is our series, and we're actually going to get the index 0 here. And that will give you index number 0. So note that if I wanted to get, for example, let's say this index here, I can pass a number 2, and we can see here we get that same value. You can see the indexes actually go up to 7,042. If I do, for example, let's say 7043, we'll see we get a key error or a value error, basically saying that a key and value error together, but basically it's saying that we can't access this index. This index doesn't exist in the series. So far what we've seen looks very similar to dictionaries. But there's some additional tricks. For example, we can slice the series using the indices. This will go from index 3 to index 10, not inclusive. So there you go, we see from our series here, we get from index 3 all the way down to index 9. So something to note is that these indices are not positions. The index, as you see right here, looks similar to positions, but if this series uses an index that were strings, then we would have to use those values. Here's an example that we can make. We can actually create our own series from a dictionary. You can see our population in dictionary, and then we're just going to define that with our different populations: California, Texas, New York, Florida, Illinois, just for demonstrative purposes. We'll go ahead and create a series by passing that dictionary into PD series, and this will now create us a little series that we can work with. And when we run this now, you'll see that population here. And now, again, this is a series, and this is the value, and this is the index. So again, almost like a specialized dictionary, to access the values to the right here, we're going to use the index on the left. So, for example, population, which again is the series, we pass in the index California, and that will give us the value associated with California. Remember, when we want to access the data from the series, we should use the appropriate index or key. Let's go back to working with the full data frame. So we can actually take our data frame here and then call the specific column with the square bracket notation. And this, again, this whole thing will give us a series. Then we can continue the bracket notation to get the index 10 from the series here. This can make it much easier to get the data without having to create a lot of variables. Now, Pandas has an even more specialized way of getting relevant data using the loc and iloc methods. So, loc is used with the index as defined in the data frame. So, you can see here we use .loc, and then we have the index followed by the column. And so running this, you can see we get the same value as above. There's also .iloc and is used with the implicit index. That is the order of the elements starting from 0. That means we only use integers. So this will get the 10th. Well, I should say 11th, since we start from 0 row in this first column. So we get the same value here. If I instead put 1 here, this would get not the first column, but the second column, again, remember, starting from 0. So you can see this is actually going to be from the gender column. And again, just to emphasize what that looks like, we'll just do a quick df.head. And you can see here, we have the first column here, the second column, and so on. And remember, this starts with 0. So that's why we're able to use, for example, 0 here to get the first column, but then the 10th row. So if I wanted to see the 10th row, so we can see, remember the 11th item is index number 10. All right, we've seen how to take data from one column, but it's possible to take data from multiple columns. You see here we have our data frame, and then we still use that bracket notation. You can see that here, except this time we have, instead of just one column, we actually have a list of the columns we care about. Now, instead of returning a series, this will actually return a slightly smaller data frame. You can see here, we have a data frame, but with just the customer ID and total charges columns. This notation is pretty typical, but sometimes you want to make things look neater and use a variable to hold our list. So, for example, we can say our columns of interest and have that be assigned from a list. And then we can use that list directly here on the data frame, and that will effectively give us the same thing as above. Note that the order of the columns of the data frame will change depending on the order you enter. So, for example, I have customer ID, total charges. We saw that customer ID is the first one on the left, and then on the right is total charges. But if I instead did total charges, then customer ID, we actually see that it's reversed. We have total charges first, then customer ID. You can even use the same column multiple times as you see here, customer ID, total charges, then customer ID. We'll see that customer ID is repeated in the order that I've put it in. We can even use multiple columns using loc and iloc. Now we still have to specify the rows, but a good shortcut to get all the rows is to use this colon notation. So this will get us all the rows and then the list of the columns that we want to get. So running this, I'll get the same thing as above or as it did earlier. We can even do this with one column, but instead have a list with just that one column in there. So note that this is very similar that we had before, where we have our loc and then specify the column, but we're actually specifying it with a list here. And what this will do, it will instead return a very small data frame. Now, compare this to if we didn't have this as a list, you'll instead see that we get series. We can also get a data frame by using our loc with the rows. So here, I'll get the fifth row, but then all the columns. And you can see here we have a series. But if I specified a list for the number of rows, you'll see instead I get a data frame. Now, this data frame is going to represent the index number 5, that row, with all those columns using the colon notation. One thing to note is that we actually don't need to include this colon here because it's going to look at the rows first. But it's usually good practice for us to include that colon to remind us that we're getting all of the columns. So if I do df.loc here, you actually see I get that series version, but with all the columns. This will be the same thing as if I did something like this. Now, as we saw earlier, we can pass in a list of rows to get a data frame, even if it's just a single item in that list. We can also use slicing with loc, so we get our index number 2 all the way to index 5. And this will also give us a data frame, again going from that second row, or I should say the third row, all the way down to index number 5. We can even combine things, for example, where we have starting with the index number 5 and going until the end. So we'll get all of the rows from index number 5 and then getting these specific columns. So this will again return us a data frame, but more specific to maybe what we're looking at or what we need. We can even more explicitly define. We can more easily define list of rows. And you can see here we have index number 1, 3, 5, and then 9. So you can see we have very specific indices for that rows. And then we have just the column here. And this will again return us a data frame, but with just those specific indexes and that specific column that we chose. Now let's move to other methods to get specific subsets using something called masking. We're just going to quickly create an example here. We haven't seen this yet, but we can actually create our data frame ourselves manually by basically taking this method pandas as data frame, passing in for the data parameter dictionary. In this dictionary, the keys will be the column names, and then the values for each of those keys will be representative of the values in the rows. You can see here we have a column 0, column 1, and column 2, along with the different values going from the top to the bottom. When I run this right here, you can see now we have a data frame with column 0, column 1, column 2, where we have the first row 1, 7, 2, which is represented by 1, 7, 2. And then you can see the second row here with 3, 2, 6, and so on. Now that we already have this example, we can go ahead and run df_example.loc, and we're just going to get all of the rows like this and getting the specific column. So far we have already seen at this point. of selecting a subset of data. It basically comes down to creating a mask, which is simply a set of true and false values. We're actually going to take our list and wrap it with this PD series. In reality, we could actually just pass the list by itself, and this will actually work fine. But by doing this PD series, this will be very similar to what we would do when we aren't doing it manually, which we rarely do this manual process like this. But it's good for demonstrative purposes. What this is going to do when we do df_example and then .loc, this would signal about the rows, and this would be about the column itself. We're getting all the columns, but this is a little new right here. And what this is going to do, it's going to give us the first row. It's not going to give us the second row. It's going to give us the third row, give us the fourth row, and not the fifth row. In this case, we'll have 1, 2, 3 rows, but all the columns. So running this, you can now see we again have the first row. Remember, starting with 0, we have the third row. Remember again, we're indexing by 0. So this is the 0, we skip number 1, we go to 2, and then we have the fourth row, and then we're not including that fifth row or index number 4. Now recall that we didn't actually have to keep this colon for the columns here. We could actually have just passed directly with the .loc, and this would give us the same result. In fact, we could actually take the whole data frame here and pass in the mask like this. Again, all 3 of these methods would actually return the same thing. Now, if we wanted to get the opposite of our mask, so in this case, we got the first row, the third row, and the fourth row, but we skipped the second row, index number 1, and skipped the fifth row index number 4. If we wanted the opposite of that, we can use this tilde mark here, and this will basically negate all the trues and false, and turns all the trues to false and all the false to true. In this case, we'll get 2 different rows, and there we go, we see the 2 rows that we excluded from our example above. Note that we could have done the same thing with the .loc, and we would have gotten the same example as above. Now that we've seen that, let's work on some real data. Here we have our df equals PD read CSV, and we're going to read in a subset of the customer of CSV that we saw earlier. Basically, just so we have only a smaller set of data to work with, but it's essentially the same data that we had before. Here's a data. It has 100 rows, so 100 elements in here. We have our customer ID, the gender of the customer, and we have some information. For example, if they had multiple lines. They had internet service, device protection, payment method, and total charges. You might note one thing here is that multiple lines, and it looks like internet service and maybe some other columns too, but they have some missing values. That's what this nan represents, basically saying there's some missing values. Let me just keep in mind as we're working with this. Earlier, we saw that we wrote manually this mask right here with this true and false. And you can imagine with 100 values like we see with this data, that would be really cumbersome. But thankfully, that's actually not how we use masks typically. We usually can build up a mask using conditionals, so we'll go ahead and show that here. Here we're going to go select the column total charges, and we're going to say, okay, go ahead and grab all the total charges that are greater than or equal to $200, and we'll set that to a variable here, so that way we can access it later. In this case, we're giving a meaningful name called my mass paid at least 200, and when we run this, you can see we have a series now that's of true and falses. Note, this is very similar to the manual construction that we made of the true and false series before. But we did this automatically by basically looking at a condition. Now we can go ahead and pass in that mask. My mass paid at least 200 in the df.loc. So we get, for example, all the rows that paid at least $200 and then getting the columns specifically of tenure. Tenure here refers to the number of months the customer has stayed with the company. Running this, you see we have now a subset of the data. It might not be immediately obvious that we have a subset of this data, but if you look closely at the index here, we're skipping things, for example, the index 2, index 4, index 97, and so on. So we're in fact getting a subset. Or you can look at the length of the series down here. It's 84, which is less than the length of the whole data frame. That was 100. So we're getting a subset. Now, if we wanted all the columns, we could have gone instead with a colon here, or just leaving that off completely. And here you can see it most obvious because total charges is not ever under $200. Now going back to what we originally wrote down, which was our df.loc, and then our mask here, and then our tenure, we got this value here, which is just a series. We could have done the same thing, but instead of using a variable, we could have done just the condition that we cared about. But usually this is a little more preferred because this part, writing out the full conditional, can get pretty cumbersome and a little hard to parse. But you can see we get the same values as well. You can use conditionals that we've learned like greater than, less than, or equal to. Python also has a few built-in methods that will create mask for you, such as isNA. Doing isNA, for example, for the column internet service, we can do isNA and basically look for any null values. As you can see here, we get a series again that either has true or false to say if there is a null value. If there is a null value, it'll set that to true. Now let me call this mask null here on the data frame. We will only get the rows where the internet service is null, and sure enough, you can see here we have in this case 1, 2, 3, and 4 different rows where the internet service is in fact null. We can even combine mask to do more complex filtering. If you look at this code here, we see we have my mask paid at least 200, which is the same as that what we defined before. But we also have a new mask here called my mask of tenures at least 30, where we check if the customer has stayed more than or equal to 30 months. Now we have these two different masks available to us. We can combine these two masks together, which are conditionals using the and operator. So you can see here the and right here. Note this is the ampersand and not the word and. This is a specific for mask that we use in Pandas. Now these masks combined together will get us rows where the person is paid at least $200 and is in fact has stayed more than 30 months. Running this, you can see we have a total charges. They're all over 200. And you'll notice the tenure are all at least 30 months. You can see we do in fact have a subset. You can see this most obviously by looking at the index and how it skips around. Now, if instead we wanted to get adults who paid less than $200, we can instead just do the opposite of our mask by taking our mask of my mask paid at least $200 and then negating it with that tilde, and then combining it with if they have stayed more than 30 months. Running this now, we get everyone who's here has stayed more than 30 months, but all the charges will be less than $200. But this returns an empty data frame, means there is no one who charges less than $200 and stayed more than 30 months. Instead, let's try to find the opposite. Finding the customer who charges more than $200 and stayed less than 30 months. We will put the tilde here before the second mask, which is my mask of tenures at least 30. Running this, and here are the results. If we instead wanted to get rows where someone has paid at least $200 or has stayed more than 30 months, we can use the or operator with this pipe character right here. Running this now, we'll now get all the rows where someone has paid at least $200 or stayed more than 30 months. You can see here, for example, we have some total charges now that are still over $200, but the tenure is actually maybe less than 30. Using these different combinations of the or operator and the negation, we create pretty complex combinations of different masks using parentheses. However, I might make this more obvious by using variables. In this case, I have the same exact stuff as above, but this time putting in the variable, my mask paid at least $200, negating that, and then using the or operator to see if they have stayed more than or equal to 30 months. I'm going to assign that to a variable called mask paid 200 or 30 tenures. Again, this is saying they paid less than $200 or they have stayed 30 months or more. At this point, you now have a great set of methods to filter your data for specific subsets. This can help you learn more about your data. We'll now get to use those tools we've learned to help us with the second step to clean the dirty data by using Pandas. The stage of cleaning data plays off the idea of dirty data. We call data dirty when the data doesn't represent the truth we think it should. This is a bit subjective, and someone's dirty data can be someone else's clean data and vice versa. Some common ways data can be dirty are when there are duplicate records, formatting issues, missing values and typos, or clearly incorrect values. We usually have to do at least a little exploring as we clean data. A good strategy when we first start cleaning is to tackle the most obvious parts first. These usually are things like removing duplicate data and addressing clear formatting issues, such as numbers being formatted as strings. Then we can focus on more complex issues, such as addressing missing values. Although identifying missing values can be relatively easy, we usually have to understand the deeper context to decide what to do with the missing values. Usually, after exploring the data for a while, we start to understand the data and its context better. This is when we can start identifying more aspects to clean, such as clearly incorrect information. You'll probably find more data issues and have to do more cleaning. This is completely normal, and it is typical to keep coming back to the cleaning stage even in the later stages like data visualization or even the modeling stage. The more you work with the data, the more context you have for doing a deeper clean. The cleaning stage covers a lot of different actions. There isn't a prescribed order that things should be done, but generally, it's a good practice to tackle the most obvious stuff first before diving in deeper. We'll learn that the simplest action we can take is usually just removing unhelpful or inaccurate data. Now, in order to clean some data, we'll have to do some light exploration. We'll go ahead and do df.head, and this will give us some information about the first 5 rows. We can already learn a lot from what's here. We can see the different column names as well as some data rows. We can probably guess what the columns represent, but you should also be careful about making too many assumptions so early. We can always look into the source of the data or ask someone about the data. So here you can see the different columns that we have, and it'll be important for us to actually ask someone about the information. Let's say, for example, you find out that this device protection column here is actually not a very important column. We'll start with removing or dropping these unneeded columns. We can do df.drop and then say what columns by columns and then give a column name. Here you'll see a return data frame, but this time without that device protection column that was here. Now note that the original data frame is actually not changed. If we do df, you'll see that our device protection column is still there. In order to save that change, we'll have to assign the output to the variable. It's generally good practice to use a new variable, such as like df_clean, so it's clear that it's been a modified version. We'll do df_clean equals df.drop and then columns, and then our device protection. Now, when we make a new cell underneath here, you'll see that df_clean will not include that column. Now note that it's common practice instead to just overwrite df. This can be clear in some situations. However, if you do this, know that you will be working with a modified version from this point, and you'll have to restart and run the code over to get access to the original unmodified data frame. We'll stick with df_clean like this. Now we could have also dropped the column by doing another method. We'll still do df.drop, but this time pass in just the column name. Let's say device protection column, then specify axis equals 1. The axis parameter specifies whether the row or column should be used. When axis equals 1, it's going to be the column. Again, df was our unmodified version, and you can see now that we have our device protection column dropped like before. One last thing we can note is that we can actually drop multiple columns. Let's go back to our df_clean here. Let's say, for example, we find out that gender in something like dependence is not really an important aspect of our dataset that we're looking at. We're just going to drop that for simplicity's sake. We can do df.clean.drop, and we set columns and then equal to a list of the columns that we want to drop. We'll drop gender, and we'll just also drop dependence. This will return a copy of the data frame with these drop columns. We'll go ahead and overwrite df_clean with our modified version, and then go ahead and print this out so you can see the difference. You can see here, for example, both gender and dependence columns are gone. We can also use the drop method to remove specific rows. This time we'll do df_clean and then drop and then specify with the index parameter which index will drop. We'll go ahead and drop this very last one here, 7042. You can see here we have one less row as before, and we can see that 7042 is no longer there. This can be useful when you want to drop specific rows that are malformed and has other issues. We could have actually done the same thing by instead of doing df_clean.drop. Then instead of specifying the index parameter, we could have said just their index in the slay 7042, but then set axis equals 0. Remember that axis, when it was equal to 1, was the columns. When axis equals 0, it's going to be the rows. You can see here our last row is dropped. Now it turns out the default is axis equals 0. We actually ran just this. We'd actually get the same result as well. We just learned how we can drop specific rows and columns. Now let's see how we can drop a set of data. One common place of dirty data is duplicated data. It could be duplicated because it was an error or simply just not useful in our analysis. In most situations, we drop data that is duplicated. So we'll go df_clean.duplicated. This will return a series of true or false, which specifies whether the row is considered duplicate or not. You can see if, for example, these are not considered duplicates. We can see these last two rows here are in fact considered duplicates. One thing to note is that it's not saying that it is a duplicate like these two are duplicates, but saying that there is a duplicate of this row somewhere in the dataset. Now by default, it's only going to show true for one row if there's a duplicate. So if there's two rows that are exactly the same, it'll only show true for one of those rows. By default, it's doing something called keep first. If instead I do df duplicated with the keep and then first, this means that it will keep the first row that is a duplicate and then drop any other rows that are duplicates. If we only want to keep the last row that has duplicates, we instead do keep equals last. You can see here our true and false values have changed. For example, number 4 here was in fact part of duplicates, but wasn't the last one. We can also specify to drop anything that's a duplicate. For example, if there's 2 or 3 rows, drop all of the rows that have a duplicate in it. This way we can say keep equals false. This basically says drop anything that had a duplicate at all. So far, you've been considering duplicates as rows that are exactly the same, that all the column values in those rows match. But maybe there are only a subset of columns that should be considered. For example, we might only want to consider if the customer ID are repeated. We can do this again with doing another df_clean.duplicated, but then specifying the subset parameter. Subset is equal to, and then the subset of columns that should only be considered for duplicates. For example, let's say a customer ID. Only duplicates are considered for the customer ID column. Now it's great that we have a way to identify duplicates, but we'll typically want to modify data by removing the duplicates, not actually keeping them. We can use what we learned about filtering with mask to get just the non-duplicates. Because the duplicated method returns true for a row being duplicated, we'll invert or negate with a tilde. We'll go ahead and copy this, for example. Now we'll go ahead and put the tilde at the negation symbol right here, and this will turn all the falses to true and all the truths to falses. This is now a mask of true when we want to keep item and false when we want to drop it when that row is a duplicate. To make it a little bit easier for us to handle, we'll go ahead and set this over to a variable. We'll say not duplicate equals. Now we can go ahead and take our DataFrame df clean and filter with not duplicate. Now, this DataFrame will now have the same thing as df clean, but drop everything that was a duplicate. You can see here a number of rows have actually gone down. Now, like we said before, it's usually good practice for us to keep track of this. We could do df clean equals df clean not duplicate, but instead what we'll do is df to duplicate equals df clean, just to make it clear that we made a new change. We saw that duplicate creates a mask that we can use to drop undesired rows. We can extend this idea to remove other data using our own custom mask. For example, we can do df to duplicate and look at something like internet service and look at any null values. It's not obvious from here if there's null values or not, but we could do a .sum. This will tell us, oh yes, there's 123 null values. There are null values we want to drop. Now remember, doing isNA is going to say if the value is null. In the case when it says false, we actually do want to keep these because these are not null. The way we can do this then is actually go ahead and do df_dedup, a bracket, and then using the tilde, it'll go ahead and flip all these falses to true and all the trues which are null values to false, which effectively drops all the null values. Reading this, we see that our data has no null values for internet service, and you can see that we have again reduced the size. We actually see there's some null values as well for multiple lines. We'll actually go ahead and do this as well for multiple lines. We'll go ahead and take this, put this inside the parentheses, and then say in the end, And we're going to do the same exact thing, but this time for multiple lines because multiple lines had null values as well. We'll go and copy this, put this into the parentheses, and then change internet service to multiple lines. Once again, you'll see that we have reduced the size of our data frame. Of course, since we want to keep this, we'll go ahead and put in df no null. Finally, we can also make our own custom mask by using conditionals. Going back to our data frame that's pretty reduced now at this point, a little cleaner. We'll look at internet service. Let's say, for example, we actually don't want to include anyone that has DSL as their internet service. We'll say df no null.internet service. If that equals DSL, we don't want to include those. You can see this will all be true. We can negate this, or we could just go say does not equal. So we'll set this as a variable to make it a mask, say not DSL. Then we'll do our df final. It's equal to df no null with not DSL. Making our final look at this for df final, we have our data. And you can see we now have only 3,751 rows, where we started with almost 7,000. Removing data is a very common practice, and sometimes data is just so messy and dirty that you just have to get rid of it. We saw how we can scrub data by removing unnecessary or unhelpful data. But sometimes we need a finer touch to get our data into a cleaner state, modifying values. I'll go ahead and import pandas, and then we'll load some data. In this case, the small customer CSV. Now this is very similar to what we saw last time, but just a little bit smaller with the number of rows and the number of columns. Like we mentioned, it's always good to do a little investigation. That's why we did df.head, which gives us some details about the data. Now we're going to actually introduce a new method called df.info. Using df.info, this will present us, well, some information about the data frame. Includes things like memory usage of the data frame, which you can see right here, as well as the column names here. Some information, for example, like their D type or data type. We can see object, which usually means string, and float 64. It doesn't really matter about 64 part, but basically saying that these values for total charges are floats. We also see the number of entries, as well as any non-null counts. Out of 100 entries, we see there are some null values because there's only 98 non-null values out of 100 for multiple lines. Similarly for internet service, for null values. Now you'll notice that for tenure we'd expect the tenure to be some number. But instead, we're getting an object, and that usually means string, which probably means that there's some malformed data. This is because Pandas tries to automatically use the best data type for the data. To investigate this a little bit further, we'll go ahead and do df.tenure to get the tenure column. Because tenure is being treated as an object, meaning a string, we can actually use the string methods here by doing .string and then doing .again to use certain methods. We can see what these different methods are by doing tab. You can see, for example, capitalized, casefold, center, and all that stuff. We're going to use is numeric. This will give us true or false, depending if the value in age is a numeric value or not. Now looking at this output right here, it's not obvious from the 100 different values if there are in fact some malformed data. What we can do is print out the specific values that show as false by first setting this series to a variable. I'll call this variable numeric, and then I'll just display the data frame with just the ones that are not numeric. I'll do df, and then using a tilde for not numeric. We can see that we are right, that there was in fact malformed data here. Specifically, the tenure was called nothing. At this point, there's different ways we can do this. We can drop this information by doing something like setting df equals numeric, so we only have our numeric data, and we drop this row. Another thing we can do is modify this value. We'll go ahead and modify it by using .log. We'll do df.log, and then doing our mask, which is not numeric, which again will just give us this one row. But if there's multiple rows, this would have also gotten it specifying the column name. In this case, tenure, and then setting it equal to some value. In this case, I want to make sure it's really clear that this is a weird value. So I'm going to use -1 since tenure doesn't really make sense to have a negative value anyway. Now, depending on the situation, you might change it to a different value. But again, here it is obvious that a tenure of -1 means that, oh, there's something special. I go ahead and run that, and note that this does in fact change the data frame. If I go ahead and do df numeric again, remember this numeric is just true and false, so it's still to get us this one row, and you can see our tenure has been changed. Now let's go back and using df.info to see if we can find some missing values. If we look carefully, we can see that there are missing values from multiple lines in internet service. Now we'll pretend for the scenario that multiple lines doesn't matter too much, so we'll ignore that. But internet service is a very important column that we need to take care of. We'll go ahead and create a mask. We'll call mask null, then equal to the df. And then our column, in this case, internet service is the column of interest. Then checking with it at dot is null. We'll print out that mask just so you can see what it looks like. We can see some null values here represented by true. Now using this mask, we can either decide to drop the null values or modify them. In this case, we'll go ahead and modify them by going ahead and using the .log for DataFrames and passing a mask and then the column itself, which in this case is internet service. And then we're going to go ahead and set any of these null values to 0. Now, this was a pretty relatively simple way for us to do this. Because this is so common, there's actually other methods to help us fill this out. One thing we could have done is doing df.fillNA and then filling it in with some value. Let's say, for example, filling it with 0. That would fill any value in the data frame that has a null value or an NA value and fill it with 0. You can see, for example, our internet service is filled with 0, but we have some multiple lines here that were also null values. We can see we filled it with 0, but if you instead wanted to use a different value, we could, for example, have this as false. Remember that this is a missing value, so this should change to false. Sure enough, you can see that's exactly what happens. Note again that this is just returning a copy. If we wanted to overwrite this, we have to do something like df equals. But we'll ignore that for now, since all we cared about was internet service. We'll make a new cell underneath here and check out our new data. A lot of different things we can do, and one of the common things we might want to do is actually replace some values. With fillNA, we saw that if we do df.fillNA, it'll fill whatever is in the full data frame with whatever value you pass in. But let's say, for example, we want just false for NA for multiple lines, but then for internet service, we wanted just 0. We did that individually, but we could do that all in one go. We could do that by passing in a dictionary here. This dictionary is going to replace values for that specific column. For example, if I wanted to fill in for multiple lines column, and I want all the null values for multiple lines to be false, and then let's say I have internet service and have all those null values equal to 0. This would do it for us. You can see here, multiple lines is filled with false. Now we actually already filled an internet service, but if this was in fact null value, it would just fill it with 0. Now if for some reason we forgot to put in a specific column, it'll just ignore those null values. If there were null values in internet service, it would only fill in for multiple lines or whatever columns we had to find in our dictionary. You now have even more tools for your scrubbing tool belt. Don't worry if at this point you feel overwhelmed with different methods. As you get practice in using specific methods, you'll find the respective code easier to recall. It does take practice whether you're a beginner or a well-seasoned analyst. We've covered how we can remove and modify values during our cleaning phase. We'll now discuss how to deal with more subtle issues and duplicates and missing values. We're going to read the CSV, in this case, smallcustomers.csv, but this time I modified the file so we can apply the next methods. There's going to be a new column called age. It's important for us to do df.head, and we'll do df.info as we've seen many times before. Now this time, we're going to be focusing on the context of our data and find discrepancies. We can see columns like age, for example, and probably have an idea of what ages should be. Looking at the info printout, we see that we have integers, which is what we'd expect. We'd expect some number or some value. Integer seems to make sense for age. This is good, but even if all the ages were integers, and we have no missing data like we see here, you might still be wondering how the data can be wrong. One way it might be wrong is if we have negative ages. Those could still be integers, and it won't be missing. Now, in some contexts, a negative value might make sense for the data, but for ages, it probably doesn't make much sense. It's important to realize when data breaks our expectations. It still might be correct, and if our expectations that are wrong, we can check if the data is incorrect by looking at the source, talking to someone who knows more about the data, or using the rest of the data to determine if it's incorrect. In cases like this, we could maybe use something like data birth column to see if there's any discrepancies and to confirm if the age is correct. Now, in this case, we don't actually have that. There's something we could do if we did have that extra data. Let's go ahead and find out if there are any negative ages in our data set. We'll go ahead and do df and then filter out all the ages that are less than 0. In other words, negative values. Sure enough, we actually see there's quite a few negative values. We'll go ahead and try to correct these and make these positive. We're assuming a little bit here where these negative values are in fact supposed to be positive. But assuming that these are supposed to be positive, for example, this is supposed to be 20 versus negative 20. We'll make a new cell underneath here, then we'll first create a mask. We'll say negative_ages equals df. Age is less than 0. Using your mask, we can now go ahead and set all the ages that were negative to positive. We'll do df.lock, our mask, and then the column age. Then that's set equal to -1 times all the negative ages. Note again that this is going to get the negative ages, and we're going to multiply by -1, making them positive, and then setting that equal to our negative ages over here. We can see real quickly if we do df that it looks all those ages are now positive. But we can double check by doing df, age less than 0, and then doing a dot over here. Because remember, this will either be true or false, and it will add up all the trues as ones, and you can see that we have no negative ages. Let's investigate some more about ages. Thankfully, there are some Pandas tools that we can use to help us do this quickly. We'll go ahead and use min and max here to figure out the smallest and the largest age. We'll go ahead and do df, age.min, and we'll do df, age.max. We have the youngest age being 7, but 411, that's pretty big. We'll be very surprised if we actually have someone who's over 400. It's probably a mistake at this point, but let's investigate a little bit further. Again, we're going to use the context of what we know about ages. We'll assume anyone over the age of 100 is a cause for suspicion and filter that out. We'll go ahead and do df, age greater than or equal to 100. We'll go ahead and wrap that around our df. We're creating a little mask here and then printing out that whole set of columns for anyone who's over 100. It's a good thing we checked if there was anyone over 100 because it looks that there's at least one other person who's over 100. Now, looking at these examples, what do you think exactly is going on here? It doesn't look like the 2 digits are repeated. This might be the case of a typo where someone accidentally pressed the key twice. If we had something like their date of birth, it'd be easy for us to confirm if they were younger than the data says. In this case, we'll go ahead and assume that those digits are repeated and that we need to correct that. In this case, this person should be 27 years old, and this person should be 41. In this case, it will be a little more surgical with our affix and edit each individual instance. We'll go and do df.lock, grab the specific index, in this case 76, and then we're going to change the age column, and we're going to set this one right here to 27. It's probably what it meant to be. We'll also do df.lock of the index 80 here. Again, changing age and then setting that equal to 41. Now we could go ahead and confirm again if we do df, age.max, and hopefully you find someone who's not too old. All good. 81 years old. That's within a reasonable range here now. Now we could go ahead and repeat this process for other columns and look for other context issues, but we'll leave that for a practice for you to do. If you find any issue, leave a comment and we'll solve it together. One thing to note is that we haven't guaranteed that the columns we examined are now clean. There could be more subtle underlying issues with the data we have yet to see. As we dig deeper into our data, we'll likely have to go back and do some more cleaning. Remember, part of cleaning is also about investigating or exploring. Remember to keep practicing. You'll find all the files you need in the description. When we explore data, we're trying to better understand the context of the data. We're looking for patterns in the data that helps us comprehend what the data is telling us. There are many ways we can explore data to better understand it. We can first investigate the numerical qualities of our data using statistics. This numerical approach can range from a wide overview of our data to focusing down to specific subsets. We'll continue to use pandas for steps like this, especially using the filtering skills we've learned to drill down into the details. We can also explore data visually. This involves creating graphs and charts to help us again gain more understanding of our data. In contrast to relying on summary statistics, we create visualizations to help us gain a better picture of what's happening in the data. This is where we can use our natural ability to take in visual information to identify attributes about our data. This can include identifying anomalies or outliers, as well as overall distributions of the data. We will continue to use pandas to help build these exploratory visualizations, but we'll introduce a couple other tools specifically made for Python visualizations. Remember, we had to investigate or explore the data before we could scrub it clean. This already shows how the phases don't have clear, sharp lines separating them. A lot of the time, we'll have to go back to earlier phases because we learned something new about our data, and this will be the case for exploration. We'll be looking for deeper patterns than we did before, which means we might find issues in the data we didn't originally notice. I like to think of the exploration phase as using a magnifying glass instead of just using our naked eyes to understand the data. But when we magnify our vision, we'll likely see the cracks in the data integrity that we just couldn't see before. At this point, we might briefly hop into scrubbing mode and quickly fix the error. This is usually the case where there are relatively minor errors that we didn't notice before. In more extreme cases, where there are significant cases of dirty data newly discovered, we'll go right back into the scrubbing stage to properly take care of it. Other times, the issue isn't as relevant to our work, and it might not be worth the time to address the issue right then and there. It could be better in those cases to simply make a note of the issue and continue with our work. Even when you decide to continue on your exploration, it's still a good idea to make some note of the data issue. This way, anyone you're working with won't be surprised if it comes up again and can address the issue if it becomes relevant, or you have some time to do some more scrubbing. At the end of the day, you'll have to make the decision on what to do with your newly discovered dirty data and what would be an efficient use of your time. All right, let's get exploring. Before we get into anything, we'll go ahead and import pandas as PD. We'll do this quite often. Before we can start exploring, we'll have to load some data. We're actually going to use this iris dataset here, which is quite famous and can be found on this website right here. Now here's the nifty trick. So far, we've been loading data into our DataFrame with PD read_CSV and then passing in the file name. It turns out read_CSV also can take in a URL. So this URL actually points to a CSV. You can hear the iris.csv, and that's how we could get our data. As long as we have access to the internet, we'll actually download this data and then get that as a data frame. So we have our data loaded. Now note at this point of the awesome framework, when we're doing exploring, our data should have already gone through the scrubbing stage. The data should be decently clean, but we'll still keep our eyes open for any dirty data. It's usually a good practice to take a quick peek at other data. We can use tools from pandas that we've learned back when we learned how to do the scrubbing. In a new cell, do df.info to do a quick overview of the data. This gives us a chance to see if there are any glaring issues that were somehow missed during the scrubbing phase. Since this data is new to us, we'll look at it over throw quick. The iris dataset actually is about some plants. They talk about different things like sepal and petal length and petal width, and also there's a column for species. Now, this is a quite famous dataset, and so it turns out that most of the data is actually pretty much clean at this point, so we shouldn't be coming across any issues. But again, we should always keep our eyes open in case there is something we find out. As we're exploring or doing other steps of the awesome framework, let's explore a little bit more. In a new cell underneath here, and we can use something like df.head to see the first few elements here. You can see here we have sepal length, sepal width, petal length, and petal width, as well as the species. You can see values here. It looks like they're decimal points. We can also do df.tail to see the last few elements. This is good because we can see the first few of them and also the last few rows. However, it might be better to view a random sample this way. We're more likely to find things in the middle of the data. We can actually do this with a sample method. We can do that with a new cell again in df.sample. Then I can go and execute this. Now this method chooses rows at random and displays them in a similar way as to head and tail. You can see here, this is actually picking a random sample. If I were to run this, again, hitting, for example, Control-Enter, you can see I get a new sample, in this case the 146th row, since it starts from 0. If I run this again, you'll see I'll get a different random samples. This is a quick way for us to look around in the dataset and see what that looks like. However, instead of running it over and over again, we can actually specify a number. We can do, for example, df.sample 5, and that'll give us 5 random rows. Here we have the 64 labeled with 63 and then some data here. It looks like in general, the sepal length, sepal width, petal length, and petal width all have numbers that looks to be somewhere around, like less than 10. Maybe there's some higher than 10. But it looks like generally they fall in that range. We can see, for example, we actually have this species and this species. It looks, as far as we can tell, there are at least 2 different species. Now, this is great, but there's one other very useful method we're going to use for exploring, and that's a describe method. The describe method will take a numerical columns and display some statistics for those columns. We can go ahead and do this by doing df.describe and see the printout. Here, we see a bunch of statistics about the numerical columns. Now there's quite a lot of information, but don't worry if you don't know what all these mean yet. We'll be going through them in more detail in a moment. Now remember, these are the columns with only numerical values. It shows things like the count, how many are non-null, the mean, the standard deviation, the minimum value, and then some other percentiles, which we'll talk about in a moment, and the maximum value. Let's start with count. That's the simplest. This row tells us how many nominal values there are in that column. We can see here for all sepal length, sepal width, and so on, there's 150 nominal values. Now, this can be helpful at this stage to get an idea of how big our data is and whether there's some data cleaning that we still need to do. After that, we see the mean row here. So this is the mean or the average for each of these columns. This statistic lets us get a feel for what's near the middle of that column. Now, there's a few ways we could also get that mean as well. We can do this by doing df and then the column. Let's say, for example, we want to look at petal length, and then we can do .mean is taking all of that column petal length. You can see all these values, and then taking the average or the mean of those values. As you probably suspect, this value should match up with what we see up here. Sure enough, that's what we see. We'll see in a moment that we can actually call all of these statistics directly, just like we had with mean here. But we can see how df.describe can do this very, very quickly for us. Now, we can also call these statistics directly on the data frame itself. But we'll see when we do df.mean, we actually get an error. The reason why is because when we do df here, we're looking at all of the columns. But note that there's no average for a species. If we did want to see the mean for all of these other parts right here, we can actually do df and then drop out the species. We'll do df.drop columns equals species. Note that this will basically return a data frame. It doesn't actually change the original df. If again I've run this, again nothing's changed, the df, so our data are safe. But now we have this drop columns here. Now we can call mean on all of these columns that can now be supported by taking the average. You can see here we have our sepal length, our sepal width, and our petal length and petal width. And if you look at those numbers carefully, you'll see that that matched exactly what we have up here. Remember, the only reason why we had to do this part is because we had to make sure that each of the columns is supported by this start mean. If we had another function here, which we'll see in a moment, and it's supported by all the columns, we wouldn't have to necessarily do this part. Let's try out some new statistics that we have in here. The next one on the row here, after mean, is the standard deviation. We can go ahead and do that by doing our df, and then let's do a column name. Let's do petal length again. STD for standard deviation, and we can see here our value right here does in fact match up with the petal length that we have up here. Now, we're not going to spend too much time going to details of how standard deviation is calculated. Without going into more detail, just know the standard deviation is a statistic that can help us understand how spread out the data is. The larger the standard deviation, the bigger the range our data for that column covers. For example, for petal width, we have 0.763, and that's relatively small, especially when compared to something like the petal length, which we see as 1.764. That means that the data in petal length covers a larger range in the petal width. Standard deviation can tell you how close we'd expect the values to be relative to the mean. A small standard deviation means that we'd expect most values to be close to the mean. Versus a large standard deviation, we'd expect more values to be farther away from the mean. The next row is the minimum, which tells us the smallest value in that column. Again, we can calculate this directly if we wanted to, either for a column or for all the columns. Let's go ahead and try that out. We'll go ahead and in a new cell here, df, and then we'll do our petal length again, .min, and you can see the minimum value which agrees with what we saw with petal length right here. We can also do df.min, and note that this won't give an error because the minimum function still works for strings, which is what the species is. It'll just tell us the first one in the alphabet. That's why we have setosa here. Going back to the describe, we see we have this 25%, 50%, and 75%. These set of percentages are representing something called percentiles. By default, describe presents us with the bottom 25th percentile, the 50th percentile, and the 75th percentile. We don't have to keep scrolling up. I'll go ahead and make a new cell here. We can do df.describe again, just so we can see it more easily. Don't worry if you're not familiar with the term percentiles. Just note that these values represent the percentage of the column's data under that given number. For example, when we look at the 25 percentile here, this tells us that 25% of the data are below this value here. That means that 25% data is less than 5.1 for at least sepal length. Likewise, if we go to the 75 percentile, that tells us that 75% of the column's data is at or below that value given. We can see 75% of the values are at or below 6.4. The 50 percentile row represents the 50th percentile, but this also has a special name. This is also known as the median, which is the value in the middle of the column's data. That is 50% of the column's data is above or below this value. We can actually get the median directly with a median method. In a new cell here, and I'll show you with df, and then we'll go ahead and do, let's say petal length again, .median. You can see here 4.35, which is exactly what we'd expect for the 50th percentile right here. Now we can actually get the percentiles by using the quantile method and passing the percentage as a decimal. Though the naming is a little confusing at first, you can confirm that the values match up. We'll do df, in this case, quantile, and I'll get the 0.25. We'll pick a column because note that if I run this right now, I'll get an error because it can't work on the species column. I'll go ahead and put petal length, and we can see we get 1.6, which is what we see for the 25 percentile. Note that you don't have to fall with the 25% and 75% and 50%. For example, I could put in something like 30%, and we'll get the quantile for the 30%, which again, isn't on the describe. It allows us a little more flexibility. Finally, we have the max row. This max row tells us the maximum value in this column. This is basically the same thing as the mean, but instead for the maximum value. Again, we can call the maximum here by doing df.max, and this will give us the maximum values for each of those columns. Again, this works perfectly fine for species because max can work on strings. We'll just consider the max value as the farthest along alphabetically speaking. Now these few statistics that we use for our methods for exploration can already give us so much detail about the data. For example, we can look at something like the petal length here and see that the data is relatively spread out. We can first look at the standard deviation, 1.76, which we can see is one of the highest standard deviations. But we can also see now, if we look at 25 percentile and the 75 percentile, that goes from 1.6 to 5.1. A pretty decent range, especially when you look at these other ranges that go from 5.1 to 6.4. The absolute range goes from 1 all the way to 6.9 here. But remember that this can include outliers. Usually people tend to focus on the 25 percentile range to the 75 percentile range. We'll talk about this a little bit more, but note that this is also called the IQR or interquartile range. Now, compare this to something like the sepal width. The sepal width has the lowest standard deviation here, which means that the values are not very spread out. We can confirm this by looking at the minimum, and the maximum value only goes to 4.4. Looking at the 25 percentile to the 75 percentile range, we can see it goes from 2.8 to 3.3, which is relatively close to that median, and even the mean here. This basically is telling us that the sepal width is relatively close and are more alike and different, at least in terms of petal length. We see how all this info can give us a better idea of our data. We'll expand our tool set to help us understand more context about the data as we explore. We explored our data using different statistics, such as the mean and median. This gave us a good overview of specific columns from our data. However, we'll often want to drill down to specific subsets of interests of our data. Thankfully, we pretty much learned all the tools we need, so we're going to do that. We'll go ahead and load our data set. So we're going to use this data set. We'll put df equals and then pd.read CSV, and then we'll go ahead and load our data set. In this case, it's going to be our customer's CSV. It's pretty natural for us to start with broad statistics and dig deeper into a specific subset. So we'll go ahead and .df info. We can see some information about our columns. So we have things like our user ID, age, annual income, and then we have our purchase amount, which we'll probably focus a lot on. In a new cell here, and usually a good one to do, is doing df.describe, and that'll give us some statistics about our data set too. So for example, we see that the median age is about 39 years old. Maximum age, at least in our data set, is 55. And then we see purchase amount, for example, ranging from all the way from $150 to $640, with the middle being right around $440. Notice it was a great start, but what if we wanted to learn more? Say we wanted to know different age group spending habits, such as young adults versus old adults, right? Now we can only know the statistics, average, median, and so on of all the customers regardless of age. So we can instead group the customers by filtering by age. We already know how to do this with pandas by using math conditionals and filtering. Let's go ahead and create two age groups, young adults and old adults. So in a new cell here, I'm going to put in young adults is equal to our DF, and then say our DF age is less than 30 years old. And then we'll say old adults is equal to DF, and then DF age as well. They're greater than or equal to 30. That defined our different subsets. And now that we have these groups, we can look at specific things like the mean, the median, or other statistics that we'd find as important. So for example, if I want to look at young adults and then purchase amount, let's say the average purchase amount for young adults, you can say that's $219. If I instead want to try out look at the average for purchase amount for old adults, you can see it's $481. If we want to instead of look at the median, we can of course do median, and you can see we can kind of explore different statistics. Now that's pretty great, but this can take a lot of typing. So instead we can use the agg method to get multiple statistics at once. So we'll go ahead, and in a new cell underneath here, we can do this by passing the name of the pandas method for the statistics we want within agg. So we'll go do, let's for example say young adults purchase amount first, because I want specifically about purchase amount, and then .agg. And then we'll go ahead and list the different pandas methods that we want for statistics. So in this case, for example, I'll go ahead and do mean as well as median. And note that I'm using the string forms here, but you could have also passed in the functions themselves. So now we can see more quickly that the young adults have a mean of $219 for purchase amount and $230 for its median for purchase amount. And of course we can switch this out to like old adults. Now this is good, but we want to keep our code flexible. For example, What if we wanted to include a new group that we want to compare for statistics? We'd have to make sure we copy and paste and not exclude that group. So let's go ahead and write some code that will loop over the different age groups. In a new cell here, we'll define our different age groups. So age groups is equal to a list where we have young adults and old adults. Looks good so far. Then we'll just do a for loop over this list. So we'll do for group and age groups, and then we'll get a statistics. So stats, and we'll do for example group, which remember will be either be young adults, old adults, .purchase amount, .ag, and then our list of statistics. So we'll do for example mean like we did before in our median, and we could add other things if we wanted to, but we'll stop at that. And then after every time those stats are calculated, we'll go ahead and print the stats. So now we have something a little quicker where we can get this output very quickly, where it goes over for young adults and old adults. So there you go. We can see, for example, we first have the young adults mean and median, then we have our old adults mean and median. Now, this is much easier for us to change our code and organize it if we wanted to change out new statistics and such. But it could be a little bit harder for us to read the printout. It might be a little hard to remember what order is which. So let's add that in there. So we'll go ahead in a new cell underneath. We'll go ahead and copy this. We're going to use this as a base. But this time we'll go ahead and define something like a dictionary, so we could define what the age groups are. So I'm going to take this age groups and instead have a dictionary, and I'm going to make it into a new line here. Remember that in Python, if you have brackets, square parentheses, or curly braces, we can actually make new lines. And what I'm going to do is I'm just going to make it clear that these are young adults by having the key young adults here. And I'll point to the group young adults, and I'll make this a new line again for us to read it easily. And I'll do the same thing for old adults, where I now have the old adults, the string old adults, and then the value will be that subset. So hopefully you can see a little bit how I might do this like in real life, where I'm working with the code. Now, this is great, but remember that we're looping over this age groups. But in this case, it's a dictionary. Before we were using a list, so we'll want to go ahead and do, for example, like age groups, and then items which will return both the key and the value. So we'll go ahead and change this part for name, which will again be the key right here. And then the group, we want to change our code too much. So our group again will either be young adults and old adults. Remember, those are represented with data frames. Now, we still can keep the statistics right here. I don't think we need to change anything, but we'll go ahead and do a little special part where we'll do print name, so we actually know what the name of the group is, and then we'll print the statistics. And then just to make it clear that we are done talking about this specific group, we'll print a new one down here, where we'll put a string of just like a bunch of dashes just to separate that out. So now we'll go ahead and loop over the same age groups, but now we're going to have some extra information just for us to see what these groups are. So there you go. It's a little bit easier for us to see. We can see there's young adults, and then we see the mean and median, and then old adults mean and median. So again, this made this much easier for us to understand. And we can see a little bit how we can more flexible possibly add stuff to it. Let's say, for example, instead of using old adults, and we wanted to have something like very old. So we could take this code, for example, and change it so old adults is not just older than 30, but maybe have a very old category. So I'll go ahead and copy this code here, but you could also change it directly. But I'm going to just make it a new style so you can see it more easily. I'm going to go ahead and define something called very old here. And then I'm going to define that with our data frame and then filter using our mask. So we're going to make a mask now where the age is greater than or equal to 45. But then we're also going to consider, I'm going to call an old adult anyone who's above the age of 30. So we'll call that df age less than 45. Now we also have to redefine old adults unless we wanted to keep old adults and very old as part of this. So remember this, old adults includes not just the people who are over 30, but also the people who would be considered very old. So I'm going to redefine old adults here by doing another data frame subset here and using our mask. And instead of doing df age greater than or equal to 30, I'll just say it's less than 45. And what's great about this, all I had to do was change our definition of age groups, and we can keep the code the same. So I go ahead and run this. Oh, I made a mistake. See, this happens sometimes. We'll go ahead and close the parenthesis here, and it tells us, hey, perhaps you forgot to close the parenthesis. Thank you, Jupyter, for telling me. And there you go. Now we have our young adults, our old adults, and now we have very old category, who in this case would be over 45. So again, this is really great because it's really flexible. Now, one thing we could do as well is maybe, for example, the statistics we're looking at mean median, you realize that maybe the median is not as important or particularly useful for the situation. But maybe you want to know how much the group has spent in total looking at the young adults in this data set, how much they spent altogether. So we can do that by passing a new statistic in this case. Let's do some. And what this will do now, we'll take each group and add up all of the amount purchased, or I should say the total purchases made. You can see here we have a nice little readout. We still have the mean here for each of the different groups, but we also have the sum, basically how much they have in total. So this can be pretty important. For example, you can see the mean is 413 for old adults. But you can see they're one of the higher values here, almost $46,000 in total compared to the next highest, which is very old at $44,000. We've already learned so much from investigating the different age groups' purchasing habits. This is the power of drilling down to groups to explore deeper nuances of our data. You can think of this exploration stage as the time you're poking and prodding the data, trying to learn more with each poke of the different section of the data. Now let's try another example where we ask a question. Asking questions is a powerful way we can structure our explanation because this leads us to a better understanding of our data. So let's imagine we're now curious about how many people from each age group spend at least $200. So we could go back to our original code that we wrote up here and then change things around. But I'm going to focus on just a subset at a time so I can kind of play around with it before I make the whole code. So what I'm going to do is actually in a new cell underneath here, and then it's going to assign group is equal to age groups, and I'm going to pull out the young adults specifically. And this way I can play with just one group at a time and then figure things out from there. This isn't probably a big deal since we only have 3 groups and they're relatively small. If you had many groups or very large data, you might want to look at just a subset at a time. We now have our group that's just going to be of young adults. And then we're going to go ahead and do our group purchase amount. And then we're going to say if they're greater than or equal to 200. This would be our mask right here. Oh, another error. I forgot to remove the underscore here between young adults since this key in the dictionary is with space in between. That's great. So now we have for that group, at least for young adults, we can see who has spent at least $200. Now what we really want to know is how many have spent over $200. There's this nifty trick in Pandas that we can actually use to count how many true values there are. We can simply just take this value, surround it with parentheses, and then .sum, and this will count just the true as 1. This will essentially tell us how many young adults have spent more than $200. You can see here we have 35. Now, this is great, but we might also consider if we want to know the exact number of individuals or the percentage within that group. There isn't a right answer, and it really depends on the question we're trying to answer. For this case, we'll say that we care about the percent of the group that made a purchase of at least $200. So in a new cell underneath here, so we can keep this value here. And so we now know how many people there are, but we want to know the percentage. So there's a few ways we can write this code. The first thing I'll do is write code to say how big this group is. So I'll call it group size and then equals our group and then just count out. So this should give us the size of the group and then divide it by our group size. So this will give us how many individuals paid at least $200 in that group, divided by that group size, and that should give us a percent. Looks like I made a mistake here. Let's go back a little bit and see what happened. So I'll go ahead and get rid of this part, and maybe I should have looked at group size and see what's going on. You see, I forgot. It turns out the group size, when I do a dot count here, it actually does a whole series. And that's not really what I want. What I really want is just the number of users here. So I can realize I can go ahead and do group and then do dot purchase amount. And this will give us just that column and then do a dot count. So if I did this right, I should get 51. So let's see if that happened. All right, perfect. So let's go back now, get this value. So I'll call it n over 200. So this will give us a number, that's why I call it n. And then it's over 200. So it's a little bit easier for us to work with now. And now I can say, okay, we can say the number of over 200 divided by the group size, and we'll call that percent over 200. and then we'll print that out just to make sure our value looks good. Cool. So we get about 68%. So this is looking pretty great, and we're pretty close to answering our question, but let's take a second to think about restructuring our code to make it more flexible. We were originally asking about how many purchased at least $200. But what if we later decided we wanted to look at how much purchased at least $500 or $1,000? We'd have to carefully change our code and copy case most of our code and change this one part right here. Realizing we might change the dollar amount, we could decide on writing a more general function. So let's go ahead and write a function like that. All right, so now we have our function that I've wrote here. So note that it's very similar to what we had above, where we have our group size. But in this case, I went ahead and made group a parameter in our function, and then instead of putting 200 there, as you can see from our code up here, I put amount. So that way we can put in a different amount depending on what we care about. So let's go ahead and run this function. There we go. So let's go ahead and test this out. We'll go ahead and do %purchase at least. So we'll go ahead and use age groups young adults, and we'll put 200 since we know what the answer should be. There you go. And sure enough, our answer gets the same thing. All right, so this is pretty awesome. Let's go ahead and take our for loop from before. We'll copy and paste this. We could have changed it directly, but I'll go ahead and copy and paste this, add a new cell underneath. And then for the stats part, I'm just going to go ahead and change this to purchased at least function. And I'm going to change this to our group because remember, we're looping over the different groups. And then we'll do 200 since we want to look at what percentage the group has spent over $200. And so we run this code, and sure enough, there we go. We get our young adults saying how much they had, which we saw 68% spent at least $200. Old adults won, which means 100%, and also very old, all of them spent more than 200, which again, they are over 45 years old. So we went over a lot of different things here, and hopefully you can see how this all forms together to great exploration. We saw how we can make code flexible and make it relatively easy to understand, also known as readability. You also saw how exploring this iterative where we ask questions, try answering those questions, and then modifying our questions or asking follow-ups. Again, the focus for the exploration stage is for us to gain a better understanding of our data. This will help us when we later model and interpret data and its results in the upcoming tutorials. So make sure to subscribe and ring the bell to be updated. And remember how we organized our code. Organizing our code can be very important. It makes it easier to make adjustments as we explore. This again emphasizes the iterative nature of the exploration phase. We'll frequently start exploring one question, which lead to other questions, or even adjusting the original question as we gain more understanding of our data. Data visualizations are another set of tools that we use to do our job as data analysts. We can split the purposes of visualizations into two, explanatory and exploratory. The type of visualization comes down to what the goal is for it. With explanatory visualizations, we're looking to present information to others. These visualizations should be insightful, accurate, and visually appealing. They might involve highlighting an insight for your audience or used to create a narrative about the data. Often, you'll simplify the visualization to emphasize the important aspects. The other type is exploratory visualizations. These visualizations are for you as the analyst to get a better picture of your data. These don't have to be perfect or neat. Exploratory visualizations are focused on learning more about the data to do deeper exploration. These exploratory visualizations are focused on discovering new patterns and relationships. These exploratory visualizations you create for yourself might later turn into explanatory visualizations that you use to convey ideas to others. We'll break down what types of visualizations we can use for exploratory visualizations. There's a great variety of visualizations out there, but we can break the visualizations we'll be using to those that focus on distributions, categories, or relationships. Let's explore these groups one by one to explore the different visualizations we can create. To begin, we'll learn about the first type, distributions. Distributions of data can tell us whether values are close together or spread out. It can also help us identify where there are different peaks in a column's data. We sometimes refer to the distribution of the data as its shape. There are a few common visualizations that focus on data distributions. One example is a box plot, which tells us what section the data falls in. Here we can observe that half the data falls approximately between 21 and 29, represented by this center box. This is typically referred to as the inner quartile range, or IQR, because it covers the second and third quartile, 25% to 75%. That leaves 25% of the data on the left side going down to about 15. The other 25% of the data on the right side goes up to about 32.5. Know that there are other outliers, data points that are well outside the rest of the data's range. They can be represented with a single point. The line in the main box is at about 26, which represents the median. Also note that although we're showing a horizontal box plots can be displayed vertically. It can take some practice viewing box plots, but it can be useful in quickly understanding how the data is distributed. In fact, we can get the same information from the box plot by instead using .describe. Of course, this time the statistics are presented by numbers. Sometimes a box plot visualization can give a quick idea of that data. Another way to visualize data distributions is a violin plot, named as such because the shape tends to look like a violin. It is similar to a box plot in that it shows a distribution, but tends to have more details on the data shape instead of just the quartiles. This violin plot is of the same data that was used for the box plot. In fact, if you look closely, you can see this version of the violin plot has a mini box plot within it. The taller vertical slices tells us how frequent the values occur. We can see more easily from the violin plot that although much of the data seems to sit at the upper half of the distribution, above 25, there's a peak of data on the lower end between 15 and 20. These are the details that can help us gain a deeper understanding of the data that could be difficult from just a numerical display or a box plot. Note, just like the box plot, we can have vertical and horizontal violin plots. Another extremely useful distributional visualization is the histogram. This graph shows the frequency of values of a column. The x-axis is sorted from small to large values, and the height of the bar tells us how frequently those values appear. This is again the same data used for the box plot and violin plot from earlier. We can already see some of the same information from our earlier visualizations, such as the two peaks we noticed in the violin plot. But we have even more detail about the data, because it's easier to tell how spread out the data is near these two peaks. Each of the distribution-focused visualizations can tell us something different about the data's distribution. Although it's the same data, they each focus on different specific aspects. Remember, you never have to be stuck with one visualization to tell the whole story. Another type of exploratory visualization, category. Category visualizations are built from new categorical data over numerical data. Think red, green, blue. Over 1, 2, 3. We're usually searching for differences between categories. We also might look at how the categories change. A common visualization for categories are bar plots, also referred to as bar charts. Bar charts look at a column of categorical values and look at a specific metric for each category, usually a statistic or another column's value. In this plot, we have 3 different species of penguins, and the bar's heights represent the species' average weight. We can see that the Adelie penguins measured were lighter on average than chinstrap penguins, which were lighter on average than the Gen 2 penguins. This is good, but let's say we also have separate data for the males and females of each species. We can still use bar charts, but this time show that male and female averages separately. This shows us something interesting. The chinstrap female penguins are on average heavier than the males. In fact, the male chinstrap penguins are lighter than the Adelie male penguins. This is something we could have easily missed from the first bar plot. Note we can sometimes gain more insight by forming a stacked bar chart. Instead of the bars for each subcategory displayed next to each other, we essentially stack the bars on top of another. This can be useful if you want to observe how much a subcategory affects each category. For example, looking at demographics in a population. However, in this particular case, there's not much more to be gained from a stacked bar chart. Relationship visualizations do, just as the name suggests, they focus on relationships. These visualizations try to display how different columns, sometimes referred to as features or variables, relate to one another. These mostly rely on numerical features, but sometimes categorical values will be included. Relationship visualizations express how much a feature increases or decreases as another feature changes. These are particularly useful for seeing changes over time. Let's look at one of these visualizations. Line plots. Line plots are great at showing how a feature changes over a continuous variable, like time or temperature. In this example, we're plotting the number of passengers for an imaginary airport between 1949 to 1960. We can observe that the overall trend is that the number of passengers has increased over time. This is great, but let's see if we can learn more. It turns out this data is broken up by month. Let's plot out the same year-by-year data for each month. Again, we can observe an overall trend in more passengers over time. However, we can also see that certain months tend to consistently have more passengers. July and August have the most passengers before going down to about June levels in September. Maybe this shows a trend of traveling for vacations during the summer months. This is the unexpected observation we hope to find when we're exploring. Our last visualization will be the scatter plot. Scatter plots show us relationship between features, but are more flexible because there isn't a connectedness property imposed like we have in blind plots. Here we plot how the lengths and widths of different flowers measured relate. Each dot represents a single flower's measurements. It's fairly obvious from this data that the length and width of a flower's petal increases at about the same rate. That is, we can draw an approximate line that follows the data. This is probably what we'd expect. As the petal width is larger, the petal length gets larger too. But this data also has what species of flower is recorded. We can augment our scatter plot by adding the species feature as a color to our scatter plot. Suddenly, we see a new and interesting relationship. Although the petal widths and lengths increase together, the different flower species tend to have a range of flower petal size. This is another way we can use relationships to better understand our data through exploration. To get started in typical fashion, we'll first import pandas as PD. We'll also need some data. And this data is going to be the tips dataset, where a waiter recorded information about each tip they received over a period of a few months. This data is small enough for us to play around with, but still big enough where we could do some exploration. After loading our data, let's do our typical df.head, df.info, and df.describe. So our df.head, we can see here are different columns and some data that goes in it. df.info, we can get a little bit about our data itself. So we can see here, for example, total bill is one of our columns, and then tip, sex, smoker, day, time, and size. And we can see that it doesn't look like we have any missing data. So 244 data points, not too big, but enough for us to explore, and they're all non-null. And then df.describe, we get some statistics about our data. So, kind of going back onto our columns here, since it's important to understand what our columns represent. We have our total bill, which is before the tip. We have the tip itself, the sex of the patron, at least their observed sex, and whether they're a smoker. The day the patron was served, and the time as well. And then the size represents the party size of the people being served. Looking from df.describe and all the statistics, we can get some information about how our data is distributed. It looks like most parties under the size part fall between 2 and 3. So it looks like from 25 percentile, and then the 75 percentile is 2 to 3, and we can see the median is 2, and we can see average is about 2.5. But there's never a party size bigger than 6. On the tip side of things, we can see the average tip is about $3, and that seems to agree close to the median. And for the total bill, we see the average is about $20, and we can see from the 25 percentile rank to the 75 percentile rank goes from 13 to about 24, with median sitting at 17. So it seems like most, at least 50% of the patrons, the middle 50%, remember this is called the IQR. So this is all great. And hopefully you're starting to get the hang of this exploration with practice. But let's introduce the new stuff, visualizations. So we can create visualizations directly with pandas, and we'll start with our box plot, which would match closely with our describe. So the way we do this is df.plot.box. And when we run this, you can see we get a box plot of all the eligible columns. In fact, there's only the numerical ones, which fits well with our describe. Now, by default, the box plots are created vertical. If we want to instead horizontal box plots, we'll do df.plot.box, vert equals false, and this will give us horizontal box plots. And you can see here we get probably similar information as we did describe. Remember, this green bar here represents the median. So we can see for total bill at least, we have about 17 for the median, and then for tip, it's probably just about 2 or 3. And that seems to fit well with what we see on our describe. And of course, with the box plot, it's a lot easier to see that inner quartile range, that IQ are going the middle 50%, going from about, it looks like 13, little under 15 up to about 25, which is again what we saw in df.describe. All the data should be here, but it's a little bit harder to eyeball that information. But it does have the advantage of you very quickly getting a feel for how the data are distributed. Now, there's actually multiple ways we can do this. So instead of doing df.plot.box, we could have done df.plot and then have the parameter kind equals box. In this case, we're also doing vert equals false because I like the horizontal box plots. And you can see we have the same stuff. Again, looking at df.describe, you can see that it matches pretty close to what we had before. And by pretty close, I mean the data are exact. It's just that it's a little bit harder to eyeball exactly this point. If you want the specific mean or median, like what exactly that number is, df.describe is probably the best way to do it. But if you just want to get a feel, which again is what we're trying to do for exploratory analysis, is we're trying maybe just do a visualization to just get an idea of how these things are distributed. Now, you might be wondering if we can choose just a single column, like maybe just the tip call column, and look at just the box plot for that. And yes, we can. So the way we can do this is we can filter out from the data frame just the tip, and then do .plot.box, and then, of course, any parameters we want to put in for box. And sure enough, we get our box plot of just tip. We can also do the same thing for multiple columns. So here I have tip and total bill, and then we have our plot.box, and you can see now we have not just the tip, but also total bill. And total bill is that sits at top here and tip being at the bottom. Now, note that when we put the columns in this order, they'll order it in this way in the box plot. If we wanted to instead have tip on the top and total bill on the bottom, we would switch the order of our columns. So you can see here when I run this code, we actually get total bill on the bottom and tip on the top. Now, there's another method we could do to select columns as well. Pandas loves its many options. We could do df.plot.box, and when we get a pass in column is equal to tip, and then any other parameters that we care about. So you can see here, we get just the tip column here, and then we could list multiple columns. In this case, we have tip and total bill, and we can see here now, we have those 2 columns in our box plot. So those are the basics of creating a box plot. The rest of the visualizations directly made with Pandas will have a similar structure as we've seen. We can actually check this out by first typing df.plot and then hitting tab and seeing all the different methods we can call from there. So there's area plots, bar charts, a bar horizontal, and then we have our box plot, hex bin, histogram, a whole bunch of things. And we're not actually going to go over every single one. This is how we can kind of do very quick plots directly with Pandas. So let's explore some more visualizations. We'll start with a question that might naturally arise. We might say to ourselves, after creating a box plot, I wonder what the distribution will look like with more detail. Well, a great visualization for that is a histogram, which again can be done completely with Pandas. We again do adf.plot, but this time cap it off with .hist. When we do this, we can see we get 3 different histograms all overlapped on top of each other. One for total bill, one for tip, and one for size. Now, this can be a little tough to read, so we can pass in a parameter alpha to make the histograms more transparent. The alpha values range from 0, completely transparent, to 1, completely opaque. We'll go ahead and set it to 0.5, so we can see those values better. When we do this, we can now see that our histogram shows up, and we can actually see our 3 histograms a little bit better. We can see tip and size actually follow very close together, which is why we have this overlap. But you can see size just peeking out over. And then we see our total bill a lot better, especially underneath this green and orange part. However, this is still a little hard to read. So we can instead take each column and create its own plot. We can use the same technique as before, but this time each in its own cell. So we can do a plot, for example, with df.tip and then do the histogram plot, and we get just the tip histogram. Then we can do the same thing for total bill, and we see just the total bill histogram, and then finally we do our size, and we see just our size histogram. If we wanted to do this all together in one cell, we could go ahead, do tip total underscore bill and size with their plot hist each on their own. One thing to note when we did create each of these plots is they each have its own X and Y axis range. So note that the size goes from 1 to 6, but something like the total bill plot actually goes from 0 to 50. So just be aware of that as you're comparing. But looking at these histograms here, I think it's much more obvious in this plot that the vast majority of people, at least in this data set, are a party size of 2. So most of the data is going to be representative of 2 people eating together. This is important because any overall insights we find will be dominated by this kind of entry. Now, when we do more exploration, we might consider looking at the party sizes separately. We might also notice that the total bill and the tips distribution, even though they're at different scales, look very similar to each other. This would make sense because it's typical for Americans to tip a percentage of their total bill. But we have to do more investigating to confirm that hypothesis. One thing you might ask is, why do we plot each histogram in its own cell versus just doing it all in one cell? Well, if we plotted all the histogram plots in one big cell like this, we actually see that Pandas likes to put all those plots in one big graph, which is fine in some cases, but note that now our range is basically meaningless to at least some of the histograms. Now, let's say we continue on our exploration. We want to look at how the features relate to one another. We can do that with a scatter plot. So we do our df.plot.scatter and then pass in the x-axis, in this case total bill, and then our y-axis column, which will be tip. When we do this, we can see we get a scatter plot where each dot represents a row on our data frame. Again, the x-axis is total bill, while the tip is the y-axis. So for example, this top point in the corner here, a total bill was $50 and its tip was about $10. And although it's not a perfect correlation, we can observe that the tip tends to increase as the total bill increases. So we can see as this total bill increases, we do see the tip increase as well. Now, there's definitely some variance in tip compared to the bill. That's why it's not a perfect straight line and more of a cloud. But this is great that we can see this relationship. However, you might find it hard to distinguish how many points there are when there are all these big clusters like this. We can again use the alpha parameter to make the point more transparent and make it much easier to observe how dense clusters are. So we'll go ahead and set our alpha to 0.25, and from this plot point, we can see where the clusters really hang around. You can see, for example, it looks like there's a lot of clusters right around at that $2 mark, and things tend to be a little more spread out as we move away from that cluster. So let's do some more exploration with another scatter plot. This time we'll observe how the tip and the total bills change with larger party sizes. So we'll go ahead and do our scatter plot like we did before. We'll do our scatter plot as we did before, but this time using size as our x-axis, and then doing another scatter plot with size as our x-axis, and total bill as our y-axis. Now we'll have 2 different scatter plots, and this can be useful, but in some cases we might actually want these scatter plots to be on one single plot. Now, this process is a little bit more work, and we'll be going over this in a little bit more detail later. But here's a sneak peek. We can use other parameters, such as label and color, to distinguish the 2 different scatter plots. And then we can also use another trick special code that we have with AX here. And we can see we set this parameter AX equals AX. Again, don't worry about this too much because we're going to be going over this later in this video. But the end result looks like 2 scatter plots colored, one in blue for tip, one in red for total bill, and put it all together with the same Y range and an X range. This gives us a nice little plot where we can observe the information all in one go. We'll go over how to create visualizations like this and dig deeper into our data using pandas in visualizations. We've seen how we can use the pandas library to not just work with our data, but also visualize it. It turns out pandas is able to do this by using another package behind the scenes to do the visualization called Matplotlib. Matplotlib is a comprehensive library for making visualizations in Python. Now, there's so much to Matplotlib that we're not going to go through all the details. We can see here more in the documentation, as well as some examples of all the different visualizations you can make with Matplotlib. We will go over enough, though, for us to understand how to make even more awesome visualizations. Of course, I encourage you to explore deeper into Matplotlib on your own. Now, Matplotlib can create great visualizations, but frankly, can sometimes show its age and feel a bit clunking old-fashioned. However, it can create some awesome and useful visualizations, especially for non-perfect exploratory visualizations. The first step is to import the library. We'll do this as import matplotlib and the .pyplot. Note that by convention, we usually import this as plt, just like we did with pandas as pd. Next, we should understand how Matplotlib's figures work. This image from the documentation has a lot of details in the parts, but the main things we'll focus on right now are the figure and axis. The figure is essentially the thing that Matplotlib produces everything on. You can almost think of it as paper for a drawing. The next part is the axes, which are attached to the figure and is where the data plotting happens. We could take multiple plots and have them on the same axis to create some complex visualizations. Here, for example, you see our figure is this piece of paper, and the axis is the thing that we're drawing on top of. You can see here, for example, there's actually two different lines, and then also a scatter plot on top of the axis. One thing to note is that we can work on visualizations from Matplotlib with two different styles, an implicit interface and an explicit interface, which uses the object-oriented style. We'll use the explicit interface because it's most flexible and basically what we've already seen with pandas so far. It usually involves using the dot notation on the axis object. We'll see this in just a moment as we start creating some plots. We will work with the tips dataset that we've seen. Just to remind us what the data looks like, we'll do a df.info and df.head. Recall that the tips dataset has these columns: total bill, tip, sex, smoker, day, time, and size. Remember that the tip is separate from total bill. And we can see a quick thing under df.head, a few of the values that are underneath that. I remember that size is the party size. Now let's go ahead and do a familiar visualization that we've seen before, and we'll do a scatter plot this time. Recall that we can do it with df.plot.scatter, and we can set our x-coordinate and our y-coordinate, and then we can set things like alpha. When we run this code, we can see that we actually get two different scatter plot visualizations, each on their own plot. If we instead wanted them to appear in one visualization, we'll have to use the underlying Matplotlib code to get what we want. One thing that I neglected to tell you is that the df.plot.scatter actually returns an object. It turns out it's an axis, and you can actually see it pop up right here since it was the last line in the cell. We can actually take that and assign that to ax, a variable. And you can see here, if I print out ax, you can see the axis object. We can use our axis object within the same cell and refer back to it inside our df.scatterplot. We can actually use this axis object and pass it into the df.plot function here to basically make those two plots now, the scatter plot and the second scatter plot on one visualization. Here you can see that right now. We can see that the key part is that we took the axis object and assigned it to the ax variable here. Then within the next scatter method, we see we have ax, which is a parameter equals, and then our variable. This will make sure that this scatter plot that's created is created on the same axis as this scatter plot. Then for good measure, we went ahead and overwrote the axis with this. Note that if we didn't include this ax part, this would still work perfectly fine. This is great now that we have our two scatter plots on one visualization. But we can do some cleaning up the visualization using the axis objects and more. This can be helpful, even though this is just an exploratory visualization and doesn't have to be perfect. By making some small adjustments, we can help us not get confused when we come back to the visualization later. Let's go ahead and start back to our plots here, where we have our two scatter plots as before, both having size as the x-axis, and then the y-axis being the tip and the y-axis being the total bill. So far, everything's exactly the same as above, but this time, we can actually take the axis that we have overwritten right here and set the y label as dollars. When we run this, you can see that we actually have dollars across the y-axis. Again, this helps us remember what was going on in this visualization. Now, we can also do the same thing by setting a title. We'll do the same exact code as above, but then also do ex.setTitle on the axis. In this case, we'll say party size, bill, and tips. When we run this, you see now we have our y-axis of two scatter plots and our title. Note that Matplotlib is really flexible, and so there's actually multiple ways to do the same thing. Earlier, we did our ax.setYlabel and ax.setTitle. We could have done also plt.ylabel and plt.title. This would actually get the same thing. Again, Matplotlib has many different options to do the same exact stuff. Now let's look at something new. We mentioned earlier about how Americans tend to pay a percentage of their bill. Let's see if we can observe that relationship in our data. We'll start with creating a new feature called tip percent. We'll do this by taking the tip and dividing by the total bill. This way, we get the tip as a total percentage of the total bill. Recall that creating a new feature from other features is frequently called feature engineering. Let's look at this new feature we've created. We can see here under describe the average is 0.16, meaning 16%. And then our median is about 15, and then it ranges from about 3% at the very lowest to about 71%. We can look at this a little bit closer with a box plot. With the box plot, we can see a little bit of that range, get a feel for what our data looks like. Again, our average and our median tends to be about at 15, 16%. It looks like the interquartile range here goes from about 13 is to maybe about 20. Then we do have some big outliers over here, but we can see most of the data fit within this range. Recall, again, that this interquartile range is the middle 50% of the data. Let's dig a bit deeper and observe the tip percentage's relationship with the total bill. Scatterplot would be great here. This time, we'll take access the total bill, y is the tip percent, that new feature to be created, and then we'll set things like some color, and then our alpha, just so we can see it easily. We run this now, we see our scatter plot. Now, we can see from this scatter plot that it looks like most tips don't range very much, basically between the 10 to 20%, even within the total bill increasing. We can see that 10 to 20%, basically that it covers almost all the tips. You might notice that the tip percent on average is a bit higher for smaller total bills, but it seems to settle into the range that as the total bills increase. Again, maybe some of these are outliers here, but it seems like most fall within that 10.02%. Let's go back and examine the distribution for the tip percentage with a histogram. This time we'll do df.hist and then does the column for tip percent, and we get a histogram. We see a very helpful visualization. The range parameter by default defines the minimum and the maximum from the data we have. We can even change the number of bins to see if it's helpful, as you can see here. When we do this, we see a much better distribution. Hopefully you're starting to get a feel for how we can iterate on visualizations to help us explore and understand our data better. Next, we'll look at going even deeper into exploration with aggregation and multivariate visualizations. In data analysis, we're typically looking at more data than we can comprehend at a time. We need to efficiently summarize our data to better understand it. This is where using data aggregations comes in. We've already used a few aggregation functions with pandas like min, max, mean, median, and sum. We've done this on individual columns and even applied the aggregation functions to sets of the column by filtering. These are some great pandas aggregation functions, and we'll see more that we can use on individual columns or features. However, usually these aggregations are simply not enough when we want to dive deeper into understanding our data. Now, we'll introduce using the group by pandas method to help us compute more aggregations on subsets of data. This operation allows us to quickly work on subsets of data and apply aggregation functions on them. The group by operation has its name origins from the associated group by statement in SQL, but it's helpful to think of it as part of the application of split apply combine first described by Hadley Wickham. Let's take a deeper look at this process. The first step that group by will do is split the data depending on the columns or features we want to group with. In Pandas, it'll be like df.groupBy, group, where group is the name of the column. This will effectively split the data frame into groups based on what column is given. Then, we'll apply some aggregation function like sum, which can be done in a few different ways. This will effectively perform the aggregation function on each group subset. This will result in a new data frame where the groups, each aggregated on their own, are combined together. Note that in our simple example, we only have two columns, one column to act as the groups and the other column that has the data aggregated over. This process would actually be applied to multiple columns from the original data frame. We'll go over this in more detail and how to select specific columns to aggregate over. What's great about using Pandas Group By is that it's quite efficient and can quickly aggregate results by subsets of data. We'll demonstrate this in a Jupyter notebook to show you how you might use this for deeper exploration. Let's do some exploring with aggregations. Since we're getting used to this tips data, we'll keep using it. We'll do just a quick df info df head to get us familiar with the data again. So again, we have 244 different data points, pretty clean data, and we have our total bill and our tip columns as well as some information about the page, for example, the sex, whether they were a smoker, the day and time that they were visiting the restaurant, and then the party size. So recall that we can actually use df describe, and that's doing actually some aggregations for us very quickly. We can even do some specific aggregations on a single column using the methods like mean and max directly. So for example, the df describe is doing a bunch of different aggregations like mean, the maximum, the minimum, the median in this case with the 50 percentile. But we can also do that directly with calling over our specific column, for example df tip, and then calling the mean, which we can see should match up with our tip from df describe, and same thing we could do with df tip, and then .max. We can even apply these on multiple columns. We can use our data frame, and then get total bill and tip undo the mean, and we can see the mean for each of those columns. But remember, these are looking at aggregations over the whole column. This can be useful, but limiting. Imagine if we wanted to see how the male and female groups differed in this data. Let's look into how we might do this with Pandas. First, let's use what we already know. We can use filtering using mask. So here we have a mask of saying just the females, at least where sex is equal to female. And we get just the data set of just those that have the sex as female. From here we can get just the tip column. So again, we're using that mask and we get just the tip column. And so now we have just the tips of people who have the sex labeled as female. Putting this all together, we can use the aggregation on that full filtered part where we're getting just the tips from just the females. So for example, I have our mean here, and then I can also do our max value. So we can see here for at least those that are labeled under the sex column as female. We have mean as 2.83, so about $2.83, and then the maximum is $6.50 for their tip. And then in a similar way, we can do the same thing with males. This case, I'll just go ahead, create a mask called male mask here, so I don't have to keep writing out this long conditional. And then we can do our mean of the tips as well as the maximum of the tips. And in this case, we can see we have an average of about 3.09. So $3.09, and then a maximum tip of $10. Now, this is a fine way to do this, but we can see that we could take a lot of extra typing, especially if there's more than two groups. Plus, when we have to retype indoor copy and paste our code, we're much more likely to make mistakes with catching an issue. So you can imagine we only had male and female, but if we had other categories in this column, we'd have to write the same code over and over, and it's just more likely to make mistakes, especially if we're just copying and pasting thing. As you've probably seen right here, is that I had to actually change it from median to max. So little mistakes like this can happen all the time. So the alternative way is something called group by. We've already been introduced to group by in a previous video, but let's break it down. We can call the group by method on the data frame and pass in the name of the column by using the by parameter. So this case, we're going to take our data frame and group it by the sex column. Note that we don't have to write by parameter explicitly, because the first value will be used for the by parameters. So a lot of times people see group by and then just the name, like for example of the column. When we run this, you'll see that we actually don't have a data frame. Instead, we have a group by object, or more precisely a data frame group by object. This object is waiting for an aggregation function to be applied to it. If you recall, this is the split step. Before we apply any aggregations in the meantime, we can still work with the data by getting just the specific columns. For example, getting just the tip column. And again, we still get a group by object, in this case a series group by object since we're just looking at one column. Finally, after we get all the stuff that we want from the group by, and then selecting which columns, we can go ahead and apply the aggregation such as mean. This will apply the aggregation to each group that was split from the original data frame, and then combine the aggregated results. So let's see what this looks like. So we see here is this is the tip of each group in the sex column. So you can see the sex column included female and male, and then we each got its averages, which if we remember from last time, we had female of 2.83 and our male of 3.09 approximately. And that agrees with what we found when we do it by hand. But you can see this is much easier to write. Note that sometimes we might want to assign the group by object to a variable so we don't have to recreate the group by object again. Note that we can still apply the aggregation function as before, like for example, we can do the group by sex here, which is coming from our group by object, getting just the column tips and then doing the mean. And we can see we get the same exact results as before. Now this is useful because we can keep using that group by object, selecting different columns or applying different aggregations. So for example, if we do tip here now in .max, we're now getting the maximum tip for each category under the sex column. And then in this case, we have our group by sex object here, and we can do our total bill column and getting the mean in this case. So again, we're having our different categories and now getting the average for each of those under the total bill. So some quick notes about an alternative method about aggregations. So we saw already that we can do something like our group by sex object here, which is going to be again a group by object and get the column, but we can call this new function called .ag and passing in the function max directly. So note that when we pass in the function, we're actually just passing the function without any parentheses at the end. This allows us to do the same thing as before, but can actually be a very nice little neat trick that can do some extra things for us. There's actually an equivalent function as the .ag called aggregate as well, and you'll see it does the same exact thing. The really nice thing about these is that they can do the apply and combine steps, but instead you pass it in like a function like max as a parameter to the function. Note that the function passed must be an aggregating function that can work over something like a series or dictionary, but that means you can use functions outside of pandas or even create your own functions. Also, another neat trick is that there are some commonly used aggregation functions like mean that can instead be passed in by string. So for example, we can pass in just the string max, and pandas knows I'm going to go ahead and run the max function or passing a mean, and it runs basically aggregation function to calculate the mean for each of those groups. Another alternative to aggregate over a group object is .apply. This has the same requirements as the function .ag and can take in a defined aggregation function or string of common function. So again, we do a .apply here, and then passing in the function max again with no parentheses, or we can pass in direct strings like we have with max here and mean. You might be wondering when you should use apply versus ag versus aggregate. The short answer is that there's a lot of times it doesn't matter. The main distinction is that apply applies a function to each group and aggregate over each column. It's a subtle difference that in the right circumstances can matter. We'll also see in a little bit that ag and aggregate can be quite flexible because you can do things like multiple aggregations at once. But before we do that, let's look at aggregating multiple columns. We might have noticed that using aggregation over a group by objects, one column actually returns a series. This is because we're only selecting one column. We can instead have the aggregation go over a data frame by using the notation of the list of columns with just one column. So you can see here we have our group by sex object here. So again, this is a group by object. We're getting just the tip, and again we see that this is just a series. But if we instead wanted to look at it as a data frame, so you can see that these are actually just series, we can instead go ahead and taken a list of columns, but with just that one column in there, this will effectively make a data frame result. So again, you can really tell really obviously that this is a data frame just by the look of it. But you can also see from the return representation, you can see it's actually a data frame, and you can actually work on it like a data frame. Let's say we wanted to apply the aggregation over the whole original data frame after grouping or splitting. When we try doing this, like for example using .mean, we'll actually get not implemented error. And you can see this is our error right here. This is because the mean aggregation function is applied to every column of the group, and some of those columns are strings. And there isn't a method to make the mean of a stat of strings. This is most obvious from the type error that we have here, where it tries to convert it over to a numeric. We can see that we can do multiple column aggregations on the whole data frame if the aggregation function could be applied to each column. So here we can use group by sex.count, and this will actually work because count can work on every single column. And again, count just tells us how many rows there are for each group. So you can see, for example, there are 87 female and then 157 male, at least in this data set. So if we go back and want to take the mean of multiple columns, we can do that. We simply have to filter out the group by object to be one of only the columns that support in this case, something like the .mean function. When we do it this time, we can see we have no issue. And again, we actually get a data frame where we have each of the categories as a row and each of the columns that we specified as their own columns with the aggregation underneath. And again, for completeness sake, the way you read this is everyone listed as a female, their total bill average was $18, the males was about $20. And then for tip, the average for females was 2.83, and then we can see for males was about 3.09. So last thing we'll do today is doing multiple aggregations. As briefly mentioned earlier, .ag and aggregate is a method for this job. We'll set up a group by object, just like before, get just the tip column, but then call .ag on it like this, and instead have a list of different aggregation functions we want to apply. Note that this can be the string form for common aggregations or actual functions in here. When we run this, we see that for the tip column, we actually get the mean, the max, and count for each of the categories. So again, this is the average tip for females, the average tip for males, the max tip for females, and the max tip for males. And then of course, how many females there were and how many males there were. So we can even apply multiple aggregations on multiple columns like this. So in this case, we'll do total bill and tip. Now this can get a little bit confusing to read, but you can kind of imagine this rectangle amount is covering just total bill. So all of this from where my cursor is all the way over here is talking about total bill versus from tip off to the right is just about tip. So you can kind of imagine this box here represents this right kind of box, imaginary box around tip. So again, this can be great for exploration, but it can get a little crowded visually. One way to clean this up is to use the .t at the end here. So again, we write the same code, but use this .t. This is what we call a transpose of the data. This essentially turns the data 90 degrees, which at least for me, makes it easier to read visually. Note that the data values themselves haven't changed. They just change positions. So you can see here, for example, our total bill mean for female and male is right here. So this again is the total bills average for females, total bill average for male. And then you can see, for example, the total bill maximum for female and then male. And then if we want to look at tips, we can look at the tip here, for example, the mean, the max, and count for each of those categories. So again, I think this is a little bit easier to read than the default output here. One last nifty trick that I like using is describe as your aggregation function on the group by object. So here we have our group by object, group by sex here, and then we're getting the specific columns, tip, and total bill. And then we could do describe, and we can get just that here. So this gives us the same info as you would have if you had a vanilla data frame. But we added the added benefit of the different aggregated statistics for each group. So again, this can be a little bit hard to read when we have many different things. So I'll first go ahead and show you just using one column here, tip.describe. And then again, I think it's much easier and understandable when we do a transpose of that. And so we can see here we have our group by the column sex here. So either female or male category. And then we have our different statistics, our count, our mean, our standard deviation, our min, and so on. And you can see that's for each category. It's like calling.describe, but for each category that we're interested in. So I think this would be really useful when we want to get quick statistics, but by groups. That's all for now. In the description box, you will find a Jupyter notebook and all links and resources mentioned. Don't forget to smash that like button, subscribe, and ring the bell to stay updated. Thanks for watching, and see you soon.